And so let's bring it back to part of the reason why you and I got to talking. Part of the reason why we got talking to Red. Red had been on a podcast of, we'll call it a predecessor of ours, and I apologize to the folks who put it together. My brain is I think it's the Flight Test Community podcast.
Flight Test Community Cast.
Community Cast, yep. I was, listening to them, and like when they were talking to Red, what he was talking about, he was explaining how you guys were going to use the concept of the Prandtl to make a Mars deployable. I mean, this was just as it was kind of being thought out, I think. And he pulled up one of those little models you had, which was just the 2-layer carbon fiber, or even a single layer. I don't even know how many layers it was, but basically that quick little roll up doohickey. And he's like, and so you roll it up to this big, and then you let it go, and now you've got a glider that's self-stabilizing, is incredibly drag efficient, or as drag efficient as you could get. And if you can haul enough payload to get data, now you can send it across all of Mars and get a far wider reach on what you're trying to learn, rather than just the one point you land and all the points leading to it. You can actually get a spray, and you can do it more than once, right? And I was like, wow. My brain just just exploded with delight. And I was like, I need to know as much about this as we can. Plus he talked about, he went into some of the aerodynamics that were the paradigm shift of weight, So why don't we delve into that if you don't mind? Can we talk about how did that journey start? Like, were you being assigned, like, hey, figure out a new thing and come up with a concept? Or did somebody say, hey, we wanted, what was that? What was the advent that started this journey of yours with the Prandtl-D?
There's a completely different place. No one assigned it to me. This was sort of downtime between a project. You go to the library, you brush up on reports and whatnot. There's this problem out there. Everybody says they understand how birds fly. I'm looking at what everybody's doing and putting these things on the back end of the airplane, right?
You're holding your hand up vertically for those who are listening. You're holding your hand up vertically.
Sorry.
Basically talking about rudder systems.
Yes, I'm talking about verticals and rudders, okay? And I know where that comes from. Wilbur and Orville Wright, they invent wing warping in order to control roll. And so the instant they do this, they have no vertical on the aircraft, and the airplane starts flying sideways and it crashes into the ground.
Right.
This happens multiple times, over and over and over.
And they're like, if we could just stop that from happening, we'd have a winner.
How do you solve that?
Right.
So they come back in 1902 with an airplane that has a glider that has a vertical on it. They started out with just one. Then later on, they put two, and they go back to one, and the one moves. And so now they interconnect the wing warping with the rudder, and they're trying to figure out literally the gain between the warp and the rudder motion. And so there's two photos that they take on October 26th, 1902. And both photos are from the back. You can see the aircraft is banked. You can see one wing looks thin and the other wing looks fat. It's because of the wing warping.
Right. Yeah.
And you can see that the rudder is deflected. And these are the first photographs of a heavier than air aircraft in coordinated turning flight.
Yeah.
Wilbur and Orville solved this. That's why those two photos exist. Wrights were very intentional about what the photos were for. They wanted to have, there would be no equivocation. Did you actually do this? they had photographic evidence of what they did. Okay.
Right. Yeah, everything
So,
they did seemed very deliberate. Obviously, pictures weren't easy. So when you took them, you made sure that they were important.
right. Glass plates, you had to make your own photographic film. Okay.
Yeah. Yeah.
So, and I, by the way, I've seen the camera that took the photo, right? It's in Dayton,
Awesome.
Ohio, in a
Yeah. Yeah.
Okay.
Sounds like we have a side trip next time.
When we go
You
to
guys go.
Toledo, when we go to Toledo, the Toledo show, maybe we should make a stop.
I'll tell you where you need to go. So, um, so Wilbur and Orville solved the problem of adverse yaw. So this is what all pilots know. This is what you
So,
use your feet for, right?
right. Explain adverse yaw, right?
Okay,
I know what
so
it is, but if you could just make a quick definition.
you roll the aircraft, and as you roll the aircraft, the wing that you're lifting up creates more drag, more lift, more drag, and so the wing slows down. The wing that you're lifting up slows down, and the other wing speeds up. So now you're rolling in one direction, but you're yawing in the opposite direction.
Right. So you're like turning out of your role.
Exactly. You're turning out of your roll. And so what you want to do is you have a vertical tail and you actually create a side force on this vertical tail and it forces the nose to go into the turn. And
Right.
this is what pilots do, and it's to
So,
coordinate the turn.
so what for those who I mean, if you're flying your airplanes, if you fly a Cub, it's a quintessential one where if you do not coordinate your turn, you will see what comes of not doing that. And the big thing as a pilot is when that outer wing is coming back, it's slowing down. It's also now stalling because it no longer has the lift it should, and that outer wing
That's
then
right.
suddenly drops like a brick, and now you're in this weird spin turn away from what you were aiming for, and it's surprising. It oftentimes creates a spin, which is hard to get out of. And if you're oftentimes that kind of situation happens as you're coming in for a landing, and that can be very dangerous if you are not ready
Really
for it.
bad.
Right. And so this is something that concerns every pilot because this is something that happens to every traditional plane.
Right.
Correct. Right. I mean, no matter what plane you're in, some have it worse. I mentioned the Cub because I everybody I've talked to about a Cub, they're like, "Oh yeah, you got to make sure to coordinate that turn." They're like, "Oh okay." And as a new RC pilot, I built this little doohickey, and I'm just flying it in, bringing it around for the last turn, and all of a sudden the outer wing drops like a rock, and I go, "Oh crap!"
Right.
I barely recover it, but I learned very quickly what it means to have adverse yaw and what the problems can be from it.
Yeah.
So anyway, continue. Thank you.
So this is, and yet you look at every single bird that you've ever seen, they have no vertical tail, and they don't have this stall spin crash problem. I mean, you've never seen a bird
Right.
in a spin. So what is the issue here? And you put that in one box, right? In the other box, you have the question of, okay, what's the minimum drag for a wing? Now, the immediate answer everyone comes up with, and you go to your aerodynamic textbooks, and it all says an elliptical load. From one wingtip to the other, you have an elliptical load right across the center. And
So
this
what that means from the very wingtip, it comes up in a parabola, basically, effectively to the center.
it's actually an ellipse.
Okay, an
So
ellipse, right? That is
and
elliptical. My mistake.
and then so at center line it's flat, right?
Yeah,
I mean it
yeah,
has to
right,
be. And then as it goes out to the tips, it actually goes vertical right at the very end.
right,
And and so this is why you get wingtip vortices. This
right.
is a huge big deal. And clear you have this turbulence. You have to wake vortex problem. that you have
Mhm. Yep.
associated with very heavy aircraft and light aircraft.
Right. And if you look
Okay.
at a lot of those aircraft memes, you'll see these very large craft kind of cutting through a cloud, and you'll see, the vortices at the tips, and they're huge. And I guess if you're not aware, and you're close to the end of a runway, as one of the large ones are coming down, you may be lifted up and thrown back down
Right.
the wake if you're not careful.
Really?
It's significant. Well, you got to think how heavy is the plane, right? Tens of thousands of pounds.
Okay.
That lift is happening by pushing air down. And if you're in that wake of thousands of pounds of air pushing to the earth, guess what?
You're
going to
right
get
at the edge of that where that pushing the air down disappears.
right.
And so
And so
it
it's
causes
also
this huge roll up right there.
right. And so you're
Okay.
in the middle of that 1,000-pound roll up, basically.
Right?
So if you're not ready, it could be dangerous. Go ahead.
Okay. So just a few years after, by the way, all this comes from Ludwig Prandtl. Prandtl is the guy who figures out, he's the first one that comes up with a tool where you can analytically calculate, if you have a control surface, how much moment you're going to get out of that. And so if you deflect the aileron this much, how much moment do you get out of that in roll?
Okay.
And Prandtl's the first one that comes up with this tool that allows you to do this. And so now you have this tool to calculate what's going on across the span of a wing. Engineer,
What
go ahead.
year is that, roughly, or specifically?
So the first time it actually gets explained to anyone, Prandtl does it on a chalkboard on June 22nd, 1918.
Okay.
And he does it for his students. And that's the first time this whole lifting line and the fallout from that, and it
It's
explains wingtip vortices. It explains, and you have this tool that allows you to figure out what the drag is
right.
across the wing.
It's a predictive tool. So now you can take that and just go figure things out on your own,
Exactly. The
which
thing
is
that,
why it becomes a prevalent solution for everywhere, right?
right. So then, once you have the tool, you can do optimization. This is the engineer part, right? You want to get the minimum drag. So it turns out that the answer is to push those vortices as far out to the wingtips as you can. And
Right.
so everyone comes up with this elliptical span load.
Because
This
that's
is,
the most amount of, we'll call it, lifting area under that
that's
ellipse,
right.
right? Like that area, you want to maximize how much lift you have above the wing. So to do that, you have to bring you want to have as much area under that lift curve, right?
That's what it leads you to,
And so everybody's
right?
like, I need to have, and so there's like the only way I got to build this plane is to maximize the lift I get,
I
and
need that.
which
And
pulls the vortices out, and I've got a predictive model. This is really easy. Let me just go build my plane, right? I want a plane to do
and
a thing. Let's go build it.
so when you do this, automatically you have this adverse yaw because
Yeah,
you have this constant downwash across the entire span of the wing. The elliptical span load is created by constant downwash. Right. So if you do this, you do it right, you end up with this same downwash at every point. And so when you say the downwash, it doesn't matter where you measure it, it's the
right.
same value no
It's the
matter where you
same,
go. And so there's only one downwash. So this leads to a series of things that you think about. And unfortunately, you get it into once you see a solution to a problem, you cannot unsee it.
right?
And so you drag this solution around with you, right, wrong, or indifferent, because you've seen this solution and it makes sense in your brain.
Right.
So here's what happens. In
It's
aerodynamic chord, there's a bunch of cascading things that come out of there. Where to place the CG. All these things fall out of this, especially if you're doing a swept wing. Okay, let's go forward just a few years. 1933, Prandtl publishes his last. Go ahead.
I was going to say, I thought you said he had 1927 or so was when that theory gets published widely.
1921.
1921. Okay, I'm sorry. It was in the 20s. I couldn't remember if it was yeah. So,
It's an NACA report.
Okay.
Number 116. Okay. So this is what happens. It's the end of World War One. All the brilliant aerodynamicists, it turns out, are German, mostly because of Prandtl. He's cranking them out. So at the end of World War One, the economic system in Germany collapses. The only way these guys can get money is if they go to Paris. NACA had established a office there where if you came in and gave your idea, wrote it out, had it written out in English, NACA would publish that and they would pay you for it. And so Prandtl does this. He publishes 3 papers. This is one of those papers. Okay. So now, by the way, in 1924, he comes up with the box wing, where you don't have any wingtip anywhere. So basically, it's a ring wing, and that has less induced drag and the pure elliptical. You still have an elliptical load, but because of the vertical part of the wing, the roll up is not as violent, and so you recover a little bit of that energy,
right,
in the wake. Right. So
you get it to work for you.
Yeah.
Okay.
1933, Prandtl publishes a new paper, and the chief historian and I used to, try and wrap our brains around this. It's just a 2-page paper. I mean, it's incredibly short. And
yeah,
the other
I
thing
read
that
it,
happens,
or at least looked at it. Yeah, it's very small. It's dense. I'll call it dense, but it's short.
Right. So why does Prandtl only? I mean, could have expanded it out to be 8-10 pages. No, he does it in 2. Why is it only 2? It turns out that he's the editor of the magazine where it's published. So it turns out that when you publish a magazine that's simple, staples in the middle, that means each sheet, each leaf is 4 pages. Front, the back, the front, and the back. So it must be a multiple of 4. One of the articles in that issue had 6 pages. So he has 2 extra pages that he needs to do something. And Prandtl, I'm conjecturing, I have a proof that would fit there nicely. And so he just puts it in there. He never does anything with that paper again for the rest of his life.
And so what does that paper do?
What he did differently this time was he said, if you have a given amount of structure, what is the minimum drag? That structure. So what Prandtl is doing now is he's no longer constrained by the wingspan. The wingspan can stretch and be a little extra wide. And what he can do is he can taper load out at the tips. So there's a funny thing happens when you do that. Okay, first off is initially from the center line, okay, that's where the lift is the deepest. What happens initially is the lift is decreasing, but it's curving downwards, and this curvature matters. Okay, so the concavity is down. So, and so at a certain point, as you're getting out closer to the tip, it flips. It becomes concave up. And then it goes all the way out to the tip. And just as the value gets to 0 at the wingtip, the slope of that curve also goes to 0. Prandtl works all the math out. This results in the minimum drag for a given amount of structure in the wing to carry that load in a cantilever wing. Okay. If you put a strut on it, you mess it up.
Yeah.
But this is it. Now, so Prandtl comes up with this first order approximation for what the structure in the wing is. And this is the key piece here. Prandtl is making a very fundamental assumption about this first order structure that's in the wing. If you do anything different than that first order simple spar skin, that's
Right.
all.
So what by
You
first
need
order
to-
you mean there's nothing fancy. It is, like you said, like an I-beam or a box and the skin, pretty much.
Exactly.
And
there's
formers.
there's no control surfaces.
Okay. Wow.
So stop
Okay.
and think
Definitely
about
no.
this. The instant you put a control surface in it, you violated that rule.
Hmm.
Okay. Now, question becomes, do you still believe that? Well, you're looking at somebody who, not knowing any better, said, okay, yeah, let's say I believe that. What happens when you do that? So the Prandtl series of aircraft, and this is all very closely related to another researcher, a guy named Reimar Horten.
Mm-hmm.
The Horten flying wings are very similar. They're like first cousins to each other.
Yeah,
And
they really do. I mean, looking at the two, like we'll call postmortem,
right,
they're not indistinguishable, but they're very close. There's a lot of similarities.
right. And so this becomes sort of and this is the mistake I made, right? During World War II, Prandtl and Horten meet. I have photographs of that meeting, and it's
Mhm.
very friendly and collegial, and I'm looking at this and I'm thinking, they're both talking about the same thing. They both must have gotten the same answer. So they both must be doing the same thing. And that's not it at all. They were talking past each other because there's a piece of this. Prandtl never got the structural part. Never did.
Okay.
I
As
could
in
show you,
never understood it.
never understood it.
Okay.
To
Go ahead.
this day, to the very end of his life, Reimar Horten could not justify why that span load should be used. There wasn't a analytical reason that anybody would believe.
So by saying the span load, it's basically saying to get the same lift, you have to go a little longer, but it produces the smallest drag for a given structure.
That's right.
But you have to have a longer wing because the lift distribution is, we'll call it, the area under the curve is less. So to make an equivalent, right?
Yes.
So to make an equivalent, you have to make a much longer wing. Based on what I saw, it looked like it was like 25% longer or so, like ballpark.
22.5%. Yep.
Okay.
You tailor the shape so that it becomes 0 at the tip.
Right.
And that is a Prandtl only. The Horten has a little bit of slope when it gets to that tip at the 0 end. So there's
Wait,
this.
when you mean slope as in the chord?
No, the slope
You mean
as
the
in the
actual
load.
Okay,
He's
the
talking
load
the
slope.
load curve.
No, that's
Yeah.
fine. I just want to make sure that it's clear
Yeah.
that because there's a lot
So
of things that it could be, right?
Horten has a little bit of slope left over. Prandtl
Yeah.
goes to 0 at the very end.
Right.
Okay.
And when it's at 0, that means there can't be vortices because there should be no difference between
Right.
the top and the bottom
So
at that point.
At that point, so where is the vortex?
Right. Where did it go? Right.
And it turns out that it's 70%. And the vortex is not a roll up like it is for the elliptical, where you step off the curb and all this lift, this downwash disappears abruptly, and there's this huge vortex. In the case of the Prandtl, you have this very large, slow turning vortex that's being controlled by the twist of the wing.
Okay, so
And
it's
so
like
you
almost
get this,
initiated by the downwash on the inward and the slight upwash on the outward. I
right.
call it upwash. I don't know if it's upwash officially, but
Well, out at the tips, it is upwash.
right.
Okay.
Okay.
So you have downwash inboard, you have upwash outboard. And so you get this is that
Slow
vortex that's
propeller almost, right?
exactly. So here's the beautiful thing of this. Okay. Uh, lift itself is m delta v. You're taking the mass of the air and you're throwing it downwards. Okay.
Hmm. That's
So this is and both the Prandtl 1921 elliptical and the Prandtl 1933, and we call it bell shaped, right? Because
right.
it's got that characteristic shape like a bell.
Like a bell
Okay.
curve that most people see in school.
Yeah,
That kind of thing.
very much so. Okay. Um, there's a subtle difference with the
Yeah.
bell curve that they use, but anyway, yes,
No,
it looks
You're
very
you're
much like
absolutely right, but I just that's part of I think why a lot of people immediately go, "Oh, that's the bell shape," because when you're
you
doing
you
a bell curve and you're watching your grades get thrown around, that's what we talk about anyway.
you want to be in that last 2.5% out there at the edge. Okay,
There
but
you go.
the this is the this large slow turning vortex. Stop and think about it. The m delta v is the same for both, but the
Hmm.
thing that you're looking at is the 1/2 m v squared term. That's energy. And this is the energy that you're leaving in the wake, which is the induced drag, right?
Okay,
So
right.
if you don't have anything controlling the roll up, like the 1921, you have this very abrupt, violent roll up in this very tight vortex core. Okay.
Right.
In the case of very slow turning, controlled roll up, you don't have that vortex core. It's this large, slow turning vortex that's slowly rolling up. And so 1/2 mv squared, saving that energy in the wake. That's why this is less drag and elliptical.
The vortex, if, to visualize it, is because if you've got downwash, say 2/3 of the way down the wing, and then you start reducing and then flip it, is the vortex, instead of being the size of the wingtip, the size of the wing? Is that why it's slow moving and so much bigger? Or am I misunderstanding that?
Or is it more the size of that, like 30% near the tip?
It's that's 1/2 of it, okay? Because that's the side that's going up. You
On
have that same amount on the
the
inside.
inside, and
Yeah.
that's
So now it's
contributing.
60% of the span of the wing is this large, slow turning vortex. So we kind of knew this. The math kind of leads you into this, right?
Okay.
So I'm gonna steal the screen again
Go
Okay.
for it.
Yep.
and allow to share screen. Okay. And
So
okay.
we're looking. It looks like wash vectors.
Yes, you can see the downwash in the middle and the
Hmm.
upwash at the tips, right?
Right.
So if you, by the way, Marko Stamenovic was the one that came up with this. And
Is he an intern of yours that did that, or?
no, Marko is one of the there's only like you can count them on the fingers of one hand, people that can do this. And Marko is a Czech Republic guy, and he does
Hmm.
this also. And Marko and I,
What,
um,
what
we're
did he do?
buds.
Is he
He
create the
he
model, or?
he developed the ability to create the twist
Oh,
on
okay.
its own, and he
You mean
and
modeled, or like actually made one, or both?
yes,
Okay.
The answer is yes.
Okay, perfect. Go ahead.
So Marco and the other guy, there's a German guy, Reinhold Stadler, and the three of us are like the ones to have resurrected this and made it a thing. So these are plots that Marco actually made.
Okay.
So um, so if you allow the streamlines to get a little bit longer, and you can look at where the vortices might be, and it kind of leads you to believe that, right? So if you were to actually build a vehicle like this and you were able to put streamers on it, you might be
Mm-hmm.
able to see where those vortices actually were.
Right. Wait, I wouldn't say it's like crystal clear, but it's very apparent that they are not,
They're not
you
at the
know,
tip.
they're not at the tip, and they're not even at we'll call it the 15% mark,
That's right.
out at the edge. They're further in.
Yep.
Did
Okay.
did you originally have any ribbons further in the wingspan itself?
We did.
So you
You
could
can see
see
where they
kind of
had ripped
where,
them off. Yeah.
yeah, okay.
On the
No,
right
no,
wing.
that's, yeah.
Okay.
I
So
love that
if
picture, by the way.
okay, so now imagine for a moment that birds actually did this. Okay. And when birds would line up their vortices, when they would fly in formation, they should fly with their wingtips overlapped.
Right. And that was the big question, right? Everybody would be like, "Hey, birds fly in formation because it must make it better or easier for them," right?
Right.
And everybody's like, "Oh, cool. So they should fly wingtip to wingtip." And everybody just looks at it and says, "Oh, of course." And then you see a picture like that and say, "Wait, that's not what's happening."
So I already told you 70% is the magic number.
Yeah.
So if you take all these birds, I digitized this photo, by the way, and when you do that, these birds, the average overlap on their wingtips is 0.68. That's how close it is.
Isn't it nice when your ideas are proven by fact?
And
Your
and
conjecture is like,
yes,
I think this might be
exactly,
what's
right?
happening.
So
Yeah.
when I present this stuff to biologists, they start jumping up and down. They are like, they are just so thrilled with this.
So
Now,
so from the biologist's perspective, what is their delight? What are they seeing proven that they've wondered forever?
because every time they tried to build a bird model, it has all this adverse yaw and they have to put a vertical tail on it. And there's no solution for that problem. And by the
Right.
way, the vortices, they when they fly those in formation, they fly wingtip to wingtip. And here you have birds flying with this overlap. And that's not what you should do. That's not the most efficient thing. And so these birds must be doing it wrong. Well, no, it's not the birds.
I
Just our
wonder,
understanding of the math.
right?
Yeah.
Or it's the understanding of what's happening.
Mm-hmm.
The,
So
the flow, because understanding ultimately what this comes down to, it's a fluids issue where we have a hard time understanding fluid flow of an invisible fluid, right?
right.
In general, just it's very difficult.
It it's not a normal sort of a thing, right?
Right. And so we're trying to we're trying to have math describe the thing we can't see, but we know the effect of. We know the thing does the thing. It weighs this much. It lifts this much. If it goes this fast, it goes. So there must be a formula. We figure out a formula, but the math doesn't really describe what's going on when we see nature. So then we go, huh, do we have something off? And, of course, naturalists are they want to build a bird that looks like a bird, probably so that they can be amidst the birds and learn, but they can't if they got a vertical tail. So, yeah, okay.
Oh,
I get it.
how can this Jeff Spedding, the vortex cores are different on the gliding Falcon. He was able to he made helium filled soap bubbles, and these soap bubbles would be very small. And so there would be these cloud of soap bubbles, and he got the Falcon to glide through the soap bubbles. And then he had these two phase locked 35 millimeter film cameras, and he took photos of the bird as it flew through, and 5 frames a second. And so he was able to figure out where the vortex cores were. But he knew that the vortices must come from the wingtips. If he had drawn straight lines through these, he would have had the right answer. But he knew that they had to come from the wingtips, and so he drew curves on his data in order to try and force
But
the vortices to come from the wingtips.
but that's not very curved data. And honestly, if I look at the curve, it's undulating about a point, 20% in or so.
Right.
And if I were a vortices, we'll call it an impeller wash, which is effectively what you kind of have, a very, we'll call it low turning impeller effectively from the way it is. Like, yeah, it would shift a little as you see it come back, right? Anyway,
This
got
is
it.
what we ended up doing.
So he's fudging his data. He's fudging the line to make it
Right.
look like what his brain says this is what it must be. But if you look at the data points, it's pretty clear.
So it's early 2015, and I'm showing this to a buddy of mine, Dr. Mike Kerho, and I'm explaining this to him, and he's getting it. He's literally sitting on the edge of his chair, and he says, "Spedding. He's in Southern California now." I go, "There's no way. This guy's at University of Bristol in the UK. He's one of the foremost bird researchers in the world, and he's got tenure there. Why on earth would he come to the United States?" So we go and look him up, right? There it is. He is down at the University of Southern California in LA, and he is the chair of the aero engineering department. He's got a PhD in zoology, but he's the
Right.
chair of the engineering department. So a few weeks after that, I went down and I spoke to the design class at USC. And when I got to this point, I started laying it on like super thick. And this guy had no chance of getting it right. And he just got it so wrong. And there are these 4 students in the back that are super mortified at everything I'm saying. And so later on, they come up afterwards and they want to know if I would like to meet Professor Spedding. And I said, I would actually love to sit down and talk with him. They're
Right.
going, okay, we're going to arrange this because we want to see this guy get slaughtered by Spedding, And so I go
So
to
was it
meet.
kind of like we'll call it a reverse psychology, where
It
like
was.
I'm
Oh yeah,
sure there's some kids in here, and that if they hear me talking crap
yeah,
about their
right,
professor,
yeah,
I'm definitely going to
right,
get a seat in front of this guy.
yeah. So
Okay, go ahead. Cool.
it's like two or 3 weeks later, we went back, and I took the chief historian with me, by the way. And so we're sitting in Spedding's office, and it's just classical British professor office. I mean, just the desk, the books, the smell of the old books, and
Yeah.
you can imagine it, right? In walks this guy, and he is about my age, maybe a little bit older, and he's very fit. He's got a Nehru linen shirt on, and he's got these khaki green cargo pants that he's wearing, and he's wearing
Hmm.
sandals. Okay, and
We're very, very discongruous with the environment he's surrounded by. Is that
um,
correct?
it for what you would expect for a British professor, not what you would expect. But for a guy living in Southern California, it's trying to tell you something.
Okay, yeah.
And so I said, Jeff, there's only one question I have. You were perhaps the foremost bird researcher in the world. You had tenure at Bristol. What caused you to come to this bird research wasteland because there's nobody else here. And what could possibly have possessed you to do that? And he just looks at me, very straight British accent. He says, well, the surfing is better here, you know. And I can just see this guy sitting on top of his surfboards, watching the California brown pelicans flying in formation, gliding in front of these waves, trying to figure this stuff out.
Right.
And so I went and he dragged in Dr. Mike Habib. Now, Mike is a researcher over at the Museum of Natural History, and he researches pterosaurs. Now, you want to talk about an animal that has these, it uses its pinky finger for the wingtip.
Right.
And stretching it all the way out there at the very end of the wing. How much load can that bird carry? That pterosaur, not bird.
Right.
That pterosaur
I know what you mean.
carry out at the tip. And you know the answer is 0. It's got to be 0. I mean, how much load can you carry with your pinky? There's no difference physiologically between you and the pterosaur. And so the load must go to 0 at the tip. And so this is all of a sudden, all these things start piling up with Prandtl 1933. And it's like, this has to be the answer.
So one of the things when we were talking earlier, you and I had a conversation a little bit before here. You mentioned that there were, right. So here you go. You talk about Horten. You talk about Prandtl, both of which have similar theories. There was a gentleman, and you said 75 or so, that was innovating the wingtip for commercial airlines. He had discovered that if you put the wingtips on, it reduces the vertices effect.
Yes.
And the vortices, and by doing so, it saves fuel. And of course, that's magic and money to all the airlines. So it's like,
Whitcomb.
Okay.
Yep.
Yeah, Dick Wickham. So you mentioned all three of these guys, and probably even like that they were all looking at the same thing.
Yes.
They were looking at it from a different angle each.
Different pieces.
And they were also using maybe a similar basis, but different language to describe it.
Yes. They were using different words to describe the same thing. And so I had these 5 papers in a manila folder on my desk. And I would, every week or so, or maybe every couple of days, or when I'm working like super hard at it every day, I'll open that up, take the paper off the top, and I'd read that paper. My head would hurt. Then I'd pick that stack up and I'd put that paper on the bottom. And I'd fold the thing up and I'd, pound my head against the keyboard because,
Yeah.
Einstein, what's the definition of insanity? I was it. Okay.
Yeah.
I kept doing the same thing over and over again, expecting a different result. And I could never, and I knew something was wrong and that there was something that was missing. And, let me go right here. This is a Whitcomb diagram. It's by Whitcomb, but you notice this one on the right side on the bottom. And do you see that vector that's forward on the left side?
Yes.
And it's a minus lowercase d, capital D. What he's saying is he's getting negative drag on that thing.
Right. It's getting a forward vector.
Right.
For effectively the lift of that winglet airfoil.
Except that remember, this thing's vertical on the wingtip.
Of course, right.
And so it's not lifting upwards, it's lifting inward.
Inward, right.
Okay. But what is negative drag?
Thrust.
It's lift. Right.
Thrust. What are the 4 forces on an aircraft? So he is getting thrust on the wingtip. Now, that negative D that's right there was not on the original paper for this diagram. I went and found it. Okay. And Whitcomb published 4 papers on winglets. And I went and I looked. I went to try and find this negative DD. And Whitcomb never wrote that down. Whitcomb never said he got thrust on the winglets.
Right.
It's like he could not bring himself to say it.
Well, you understand industries like this, though. If you're saying the thing that nobody believes, you get told you're a quack, and
I get told that all the time.
right, and your ideas get thrown to the wayside. Like, you must not know what you're saying if you're telling me something I don't want to hear. It seems to be a popular thing. An example in archaeology: there's some archaeologists who went down below the humanity line, as it were, because nobody existed before a certain time, so they started digging deeper and they started finding artifacts, and they're like, well, humans must have been here for far longer than we think. And the answer was, no, that's not possible. You must be contaminating your site, because I don't want my work to be discredited or blah blah blah. You couldn't possibly be right, even because I don't want to believe it. Is kind of, and it seems to be a prevalent way to do business, I guess, in researching fields. Your volume went down. I don't know if I'm talking over you or.
Sorry.
No, there you go. It's there. You're good.
Okay.
So and I say that because I know that you, I'm sure, encountered a lot of the same kind of thing. Because heaven forbid you come up with a new way to look at a problem and find solutions that are evidentially correct.
Right.
You went and said, okay, well, I'm going to test it. So you tested it, right? So how did you go? I guess my interest here is, you've got all these people who are saying these things. How did this connect with, wait a second, this means thrust? This means something else is going on. We need to test this because it could have a big impact.
And right there was the thing that convinced me it was thrust.
The negative DD, or just
That's
that vector diagram.
That vector diagram and the minus DD. And that was the part, I only have a 3-position switch. I tell my interns this all the time. My 3 positions are dim, flicker, and off. And because I'm not that smart. And so there's this moment where, you have this flash of insight, and it's like, of course it's thrust. It has to be thrust because it can't be drag. The reality is there really is just a little bit of drag at that point. But the lift vector is tilted so far forward because of the upwash,
Right.
that little tiny bit of drag doesn't show up.
It's not enough to counteract the thrust that's coming
Exactly.
from it. Right. So there is, in fact, an actual thrust. Now, if it's in level flight, the thrust on each wingtip or wing edge, whatever, if you flatten the winglet out, you pretty much have what we're talking about with the Prandtl.
Exactly.
It's even, so you don't see a yawing action. But when you deflect a surface, you get a different lift vector. And when you increase, the reason why the one wing goes up when you do the roll is because you're creating increased camber. It creates increased lift. That lift vector is slightly
Tilted
forward. So therefore you have thrust as a result, as well as lift, right? Your lift vector is forward and whatever. And yes, there's drag. And going by deflecting downward, you do create a little bit more drag, but it's clearly not more than the thrust induced by the increased lift.
Exactly.
The downward one,
as you lift
the downward
that wing up,
yeah.
As you roll, you have this additional thrust. And remember, your wings are longer, so there's a bigger moment arm. And so it pushes that wing forward. And this is why birds do not need vertical tails.
Right. I mean, they use it to assist in that, probably to speed up the turning. Right, because they do twist their tails and kind of move them up and down a little bit. And I know that kind of helps, probably, because what I noticed is when you're one way in the turn, turning the other way is an event. It is something you start early and often. And as you come around, it starts to bring it back to level, and then it starts doing its proverse yaw. This is me just flying the wing that I built, that using the same principles. It flew exactly like yours did, at least in visual. What I noticed is when you're banked one way and you want to turn the other, takes a minute to get there.
Get a little bit of side slip. Yep.
Right. You're getting side slip, you're doing a bunch of other things, and to come back around is not, it's not as snappy. Right. That is the
No.
one thing I'll notice. It's not snappy. You can definitely do the slow and gentle, which is actually one of the most majestic parts of it. But I have a feeling that birds use that tail to help kick the counter turn
So
quicker.
birds that
Because
need
it's not a
maneuver-
rudder, but it's like a quick kind of bump so that it gets turned. Because I noticed once you get to a certain point, like the turn goes like it should. But to get to that point is hard with just the aileron deflections. So I wonder if that's what you know what I mean? Go ahead.
Hang on.
Okay, so keep going.
It turns out that birds that need to maneuver will use their tails in this way. Okay. So raptors in particular will have large tails and they will tilt it and they will use it in order to get some moment out of it. But if you figure out the tail volume that they have,
no, it's small.
It's very small. And one additional thing, the bird with the longest wing is the albatross, and it does not use its tail in this way at all.
No, not at all. What I noticed with RC aircraft, when you're needing to do a quick bump in direction, you kick the rudder, and in the first couple seconds, you get the largest kick out of the tail. So if you're looking to kind of roll it one way or the other, and you're using a 3-channel, right, where it's just rudder and elevator and the thrust. So when you do that first kick, it comes out a certain way, and that changes the attitude and a lot of the other factors. So that's what I'm thinking. My conjecture is that that little bit, the tail on the bird, when they widen it, turn it, and maybe like kick it up a little bit, it gets that initial push, and that's enough for the rest of the natural effect with the outboard, we'll call outboard thrust from the turning, actually helps it come around when you're trying to turn the other way, right? When you're going, I'm going to the left, now I want to turn right. It takes a bit to get there. But if I want to do it quicker, I use my tail to just get that started. It's not going to do much after that initial kick. But once I've got it kicked, I've turned it over enough where the outer wings do its job. And you get that natural graceful turn. This is me just kind of connecting dots. I apologize.
There's a book that was written by a gentleman named Carl Coford, and he wrote it's about the California condor, and he studied the California condor and came up with a bunch of observations about maneuvering with the tail.
Okay.
On the condor, and your observation is fundamentally in line with what he found. And Coford died many years ago. He wrote the book originally in the 1940s, but during World War II, nobody was interested in publishing it. It didn't actually get published until about 1950.
Okay.
Definitely worth having.
Okay.
Okay. Real quick.
Yeah.
Imagine for a moment that you're on a perfectly glass smooth lake. All right. You're in a powerboat. Okay. You start moving forward with the powerboat. Okay. There's a bow wave that builds up. Now imagine for a moment that you have two surfboards that are riding on that bow wave. All right. Now you're going to connect those surfboards to the bow of your boat and press down on the surfboards just a little bit. So now the surfboards are riding along on that bow wave, and you're getting a little bit of energy out of that and feeding that back into the boat and reducing the drag of the boat. Okay?
So you're saying the surfboards are on the forward edge of the bow wave.
That's right.
And they're riding down the bow wave.
Yep.
Producing thrust from basically they're riding downhill and forward. And that's producing thrust for the boat.
Exactly. So here, remember, there's no part of the boat that's down there underneath pushing those bow waves up. It's a rebound that's happening because of the displacement of the water at the center. And so Prandtl's 1933 span load does the same thing with air. It's the rebound of the air that's causing this upwash at the tips. Okay. So now one last thing, if I take those surfboards and I press down on one surfboard a little bit more than the other, I can steer my boat. This is Prandtl 1933.
Because that man was a fluid dynamicist, not an aerodynamicist.
Yeah. And so my buddies send me this.
Hey, he's showing us a picture of what looks to be a motorized surfboard with the dog on it, hanging out with his owner, who's on a lawn chair, sitting on it, enjoying every minute.
It's actually not motorized. He's actually just surfing on the wake of the powerboat.
Oh, okay. Okay. So he's behind a powerboat.
Yeah.
Riding the front edge of the wake and enjoying the crud out of that.
Yeah. And the dog is just sitting there.
Yeah. Having a good time.
Just chilling.
Yeah.
This is what my buddies do just to harass me.
That sounds like good buddies.
Okay, hang on a sec. Let me give you back control of your podcast here.
Are you kidding me? All we wanted to get you on, you're in charge now.
Okay.
So no, that's fantastic. I mean, so we're all following along. We've got the outer edges are basically your steering and because they're riding the wave.
Right.
At the wingtips, it's reducing the drag from the rest of the boat coming forward. And I say boat, but as an airplane, right? That's the
right.
Okay.
So now I want to make your head hurt some more.
Yes, please.
Mine started hurting about an hour ago. Matt's doesn't, because Matt's been studying this for a few years.
I specifically have been trying to learn as much about aerodynamics, not just because of this, but I want to get this. And so, trying to understand when we did our aerodynamics episode, that was a real big help in understanding the details of some of this nonsense. And I call it nonsense, but I really mean magic and amazing.
Can you see this?
Yes.
Okay. So if this works for a wing, it's got to work for a prop.
Of course.
Now, the one thing you don't want to do with a prop is increase the diameter. So it causes you to abbreviate the way you do it. And so you end up with this, it has to fall off dramatically out at the tip. So we actually built this thing.
So wait a second. So you're basically widening the inside of that bell.
Yes.
And shortening the lower ring.
Yes.
Kind of the lower crown.
And it's actually very abrupt where you change from one to the other. Okay.
So you're looking at, like, instead of a 20%, right, where the shift happens, right? It's more like 10.
It's actually it's close to the 20% sort of number.
Okay, as opposed to 30. I think we're talking about.
Right.
Okay, go ahead.
So, but what you end up doing is you load up the inner edge of the prop. Stop and think about, if you're trying to reduce what if you treated propulsion as a black box, what is it that you put into the black box? You put in power. What is it you get out of your propulsion system? You get out thrust.
Thrust, yep.
You put in power, you get out thrust. So what if you held the thrust the same and changed the twist on the blade? And that's the only thing. You don't change the plan form. You don't change the number of blades. You don't change the RPM. You don't do any of that. You only change the twist. And then you try and minimize the torque.
Okay.
Okay. this is what you get. 15.4% more efficiency right off the bat. Okay.
So it's not changing, we'll call it the pitch of the propeller per se?
It does change the pitch, but the RPM is the same.
Okay.
Okay?
Yep. Nope. So same motor throughput,
Yes.
right?
And
It's turning the same amount.
You're holding the thrust the same. You're holding the RPM the same. And you're minimizing the torque. There's a kicker that comes with this. Do you see how it rolls off at the tip and the load drops off at the tip? This thing is 88% quieter.
Oh, yeah. Yeah, because you don't have the vortices. The vortices are what creates the noise.
Exactly.
Well, I mean, they're there, but it's significantly lower, right?
So this is, we actually built a few of these. We also built a fan, and you can see what happens at the tip, how it rolls off at the tip. This fan, 88% quieter than the original fan.
I'm trying to see, like I see it. There's a significant twist between inner and outer.
Yeah, you can see it there in the CAD drawing.
Yeah, it's a lot easier to see there.
Yeah.
And that makes all the, because I guess normally what is it? Basically almost a flat plate, more or less.
No, it was they were beautifully made blades on the original, but it's called minimum induced loss, and that is the way all propellers are made and fans are made, is this minimum induced loss. But that's not what we're doing here.
Right. You're breaking my brain and I love it. But
yeah, this is all you, Matt.
Okay, so
is it? Oh, the question that came in just now is that a ducted fan, and does that affect if there's a shroud?
This is a ducted fan, and the last thing you should do on a ducted fan is load up the tip, which is exactly what ducted fans do, because that dramatically increases the amount of torque that you need for the amount of thrust that you're producing. I'm doing the exact opposite. I'm trying to unload the tip.
Right.
And that's what makes it quieter.
So would that typically, given you're keeping the same diameter, so you're not changing, so you increase the amount of flow and reduce the noise.
Yeah.
Same diameter, same spinning power.
Same thrust. Okay.
Okay.
And same RPM.
Okay.
Now here's my inexperience and ignorance showing. Wouldn't an increase in flow be an increase in thrust?
It is.
That's what I was thinking.
It's not a 1-for-1.
Okay, right.
Because remember, I'm not increasing the flow out at the tip because I'm unloading the tip. So that means I have to increase the flow inboard.
Okay. And it comes out, pun somewhat intended, it comes out in the wash.
Yes. Yes.
Well done, Joe.
I appreciate that.
Wash. Okay. But so imagine for a moment that I gave you a bowling ball and told you to carry it outside and put it in the trunk of your car. None of you would carry the bowling ball straight out to the side in the air, right? You're going to let it hang down next to you or hold it in close to your chest. You're trying to minimize the torque that you have to exert in order to carry the bowling ball. It's the same thing.
So
we're moving the load of the wing, or in this case the propeller blade, inward.
Yep.
So I'm gonna, and I may be jumping ahead, but this seems like a good time to bring up this question that someone has asked, it might have been Devin. One of our
Mhm.
listeners asked it in our chat channel before this, and it's, I guess, the quintessential question around all this, and it applies to the wing and now to the propeller, which is, if it's true, why aren't we doing it?
Yeah, there's a lot of questions that basically say, okay, this is pretty amazing. Why the slow adoption?
Um,
I can tell that this is a far more complex problem to solve than the elliptical load,
yes,
right? This is not a simple, you just solve this, whatever, solve this equation, be done.
right.
You have to,
It doesn't
you,
work that way.
you do more than this. You can't just say, hey, load it like this. You'll solve for D, solve for LD, you solve for
Yep.
your V's, we'll be good, call it done. Your prop has to push this far or this hard or whatever. This is the thrust you need. And you can just keep going now. It's, hey, you want to do this. This is what you need to do to the whole wing. You have to design each piece of it, right?
Yeah. And your compressor blades are all this way, or all of your props are this way. Now, there's if you put this one piece on top of the other and couple all these things together and actually put them all together in one vehicle, you get a 70% decrease in the amount of drag that you produce.
What kind of fuel fuel efficiency is ultimately what people give a hoot about. When you reduce drag by 70%, the fuel efficiency does not go up linearly, correct?
No,
Right. You're
no.
looking at a
You,
fuel efficiency savings of what, half of that? Which is
uh,
significant, by the way. I'm not
it,
trying to belittle it. 70% drag reduction is amazing, right? When we're looking at big airliners and they're trying to quibble out an extra like 3%, right? And they're delighted when they can get a savings of 3% from drag, right?
there's a problem that you run into as soon as you start talking about um, airliners, and the reason is um,
This is
you,
one of the questions people have, by the way.
absolutely
The
okay.
airliner question.
You end up saving a little over 50% on fuel.
Whew.
All right.
Whoa.
So here's the issue.
Oh yeah, I
The
was gonna say,
instant
what's the issue
the
there?
instant you start saving fuel, what do the airlines do? It turns out that their best operating point is not the most efficient operating point. And the reason is the airplanes are financed. And so time is money. And so you're willing to sacrifice some fuel to fly too fast in order to help pay for the thing. And so your 50% becomes a number more like 30% by the time the airlines get all done. But
Okay.
they end up flying at 0.92 instead of 0.87.
And 0.87 is what they would fly at if they adopted,
Yes.
versus 0.92, which is what they fly at currently.
Yeah,
And
that's what you would
those are
do it.
that's a mock number,
Right.
just so
Yeah.
everybody's clear.
Yeah.
Wow.
So this is it and
And I
have
appreciate you going through it because I know that the the drag efficiency is incredible. That's a big giant jump. And I understand that fuel efficiency again is a far more complex problem. And I appreciate that you were able to give us the 30% number,
yeah.
obviously ballparking it, but it's still significant savings, right?
This is definitely you're going to do this. More I could see where 85 to 90% of all aircraft should use this idea.
Right. So,
No
so
question.
what? Okay, so what are the drawbacks then? Right? Because there is there a drawback to the system that other than the complexity of design? Although with today's modeling techniques and things like that, I think once the procedure gets understood, that becomes an easy thing. Like there's a lot of complex things we do in structures, right? But they're knowns. We know how to do them. They're a pain in the butt, but we know it's this. You iterate, you do the other thing, you iterate again, and then that if that, the deltas get small enough, you can go ahead and use it, right? Like that's I imagine it's the same way with the aircraft designs.
Aircraft design, okay, stop and think about it. You're manufacturing straight lines and square corners are cheaper to manufacture. And and so that's a piece of the puzzle that is not wrapped into here. And
Right.
not being a structures guy, I don't have that background. I'm just looking at it from an aerodynamic standpoint, although I am taking into consideration this first order amount of structural
Mm-hmm.
model that I
Hmm.
have in order
Sure.
to minimize the amount of drag for that first order structural component.
No, I get it.
So what I'm hearing is, while there's massive benefits to it, when you take into account um, development costs, manufacturing costs, time lost in the air, or increased time in the air, so you're not getting the turnaround, you're not flying as many people as quickly, and perhaps one or two other factors that haven't been discussed. All offsets is not a straight, fuel efficiency is money. All that offsets and is not uh, tantalizing enough or not worth enough to go through that process.
Or
Yeah.
maybe just not as straightforward.
And okay. And the one other thing, okay, let's like talk about, let's say you have two choices when you're talking large airliners, right? There's company A and there's company B. All right. And we deal mostly company B here in the United States.
Mm-hmm.
So imagine that company B had just invested in a huge amount of money to be able to build a composite fuselage and where the parts are being built at other places, and then those pieces come in and they can bolt the whole thing together, and that's what they're producing. And they had to come up with an entire new line and an entire new process to do all this. All right. And they spent, let's say they spent $2 billion. Actually, I think the number's probably closer to 20 billion. But let's say it's $2 billion.
Factor
All
it in.
right. Yeah. Well, you look at the stock prices and you look at the amount of investment and you look at what they've predicted for their costs and you go, you can't make it for that. Okay. And you work through the math and you go, it's got to be in this sort of a range with this, you know,
Yeah.
number of zeros. But
Yeah.
but you so when you sit down, you say, okay, then how many do they have to manufacture over how many years in order to recoup that cost?
Hmm.
And the last thing they want is a new design that's bigger, better, faster. And that is a threat to the long-term the corporate bottom line. So what would you end up doing? You keep building what you've always built.
Boo hiss. I
Okay,
guess I'm a fan of
Hey,
innovation, but I also understand
business
like
is in business to make money.
I know. I know. Still boo hiss.
you can't blame them for that.
No,
No,
I recognize that it's the reason things happen.
Okay.
But anyway, cool.
So let's say you did all this stuff.
Right, because
How
that's the
close-
postmortem, right? That's the postmortem of this. Is
Right.
okay, you've proved this. This is real, and you actually understand, because what you did is you took what has got to be what a shoestring budget to test this. You grabbed as many interns as you could, which, by the way, kudos to you and kudos to your team. Was your team primarily aerospace engineers?
About half were aero engineers. I had some real unusual ones. I took a few people that were not technical degrees because they were debating whether they were going to become engineers or not. And I was trying to pollute their minds, and you know, and I didn't always succeed. Um, so in these photos right here, one of them became an F-18 pilot for the Marine Corps.
Nice.
One of them became a weapons system officer for a destroyer. And there was another one that ended up, he was a special operations. They, you could not ask for a more spectacular group of students. By the way, this one, there's 1, 2, 3, 4, 5, 6. There are 6 PhDs in this group, and I'm not one of them.
Wow.
And it was ridiculous the number of students that my students that ended up getting PhDs.
So did you inspire them, you think, to further on and go deeper into what
I think
they were
so.
passionate about?
I
Because I mean,
think
that's
so.
really what a PhD is. It's like, I really love, I want to know more about this, and then they just go diving
What
deep.
makes it tick? How does
Yeah,
it work? Yeah,
yeah.
that's what we were trying to do.
Congratulations, by the way.
Yeah.
That's good. Good on them and you.
This one all the way down here, you see the Concord replacement proposal grad student,
You
2022.
you need to move to your left.
Okay.
There we go. Got it. It's the
Ye-
yellow building
ye-
there. Got it. Yep.
Yeah. That's Cranfield in the UK. And that guy, I first encountered him. He was in the National Institute of Technology in India. And he wanted to know what it would take in order to come to the West and do this kind of work. I
Right.
said, coming to the US is going to be hard. But if you go to the UK, they will recognize your degree, and you stand a good chance of getting an advanced degree out of it, and that will open all sorts of doors for you um, coming to the
And
West.
when you say advanced degrees, is that once you get your master's, then
Yeah,
to do a PhD, you can pretty much then you choose.
yeah. And
Okay.
so that's what I told this kid, and this is when he was getting his degree at Cranfield. And
Nice.
he was on the Concorde replacement proposal. And we have the ability to now design Prandtl wings for supersonic flight.
That was a big question somebody had asked me, and
Yeah,
I'll see if I can find it. But basically, they were wondering: is the regime limited to subsonic,
it is
or
not.
can it be extended to supersonic and or transonic?
It easily transonic, and it turns out it works for supersonic. And
So,
so, go
does
ahead.
is there a big shift in how it gets designed, or is it really just sort of almost like a linear translation? I know that they're very different regimes, so I'm sure it's very
It's
different.
not linear, but the equations are reasonably well known, and this guy
Mhm.
incorporated them. And
Oh, okay. So he took that and verified that it would work transonic.
yeah, and
That's
so
awesome.
in June, he came out for a whole week. He flew from London and spent a week with me. And we toured all of Southern California, and we went to places and talked to people. And he got like the it. He got to go to Virgin Galactic, and
Wow. Yeah. Yeah.
I mean, just stuff that just doesn't exist in the UK, and
Right.
it was an amazing,
Well, I mean,
amazing time.
there's so many, we'll call it famous or top end airplane designers or companies out there that, I mean, it's really kind of like there was clearly a hotbed at a certain point. Like, no. If you're going to do this stuff, you got to be here, or there's a couple other spots in the US, but the California is a really incredibly dense space for that, which I'm always kind of impressed by.
The model shop guys, I
Yeah, Red
so
and his
all those
crews.
students and all the model shop guys, it never would have happened without every single one of them. I
Right.
kid you not. This is more them, so much more them than anything I
Right.
did. And it just simply would not have happened without them. I love
So
that photo.
It's cool.
So how hard was it to transfer the load, the elliptical, the bell, sorry, yeah, the bell loading, and to figure out how you selected each airfoil for that, well, for that section, right? Because you're basically looking at like, okay, for this regime, I need this kind of airfoil. This one, I need this one, and it's got to morph. Or was
There's a
it?
piece here that I haven't told you yet. When I was a grad student, working for NASA, they had a new computer program that would design airfoils, but it did something that was very unique in that there was a professor in Germany that
Mm.
figured out how to go from this is the aerodynamics that I want. What's the shape that gives me those aerodynamics?
And
And
you're
the
talking about
professor,
like, I want L over D to be this. I want the L, those different characteristics. Is that what you're referring to? Reynolds number this.
actually, it's more fundamental than that. How much
Okay.
laminar flow can I get over the upper surface and the lower
Okay.
surface?
Okay.
So you and what lift coefficient would that be at? And so
Okay. Right.
you can put all those things into your design. Okay. The professor had the technique to do it, but he did not have the skills to be able to write code to do that. So he had this guy who was interested in sailplanes and who had come to Germany, and his name was Dan Summers from NASA Langley. Okay.
Uh-huh.
So the Summers sat down and wrote the code basically for this professor. The professor's name was Richard Epler.
Oh, wow. Yeah.
Okay.
I
My
mean,
how the
So
pieces come together.
so
the
Summers,
Epler 749 is the airfoil that I'm using for the glider. Go ahead.
bingo. Okay. So Epler, um, his friends could call him Dick. We called him Professor. All right.
Gotcha.
Um, yeah, so there, and he was very stiff, proper old man, but he and Dan got along very well. Me, maybe not quite so much.
He tolerated you on a good day.
Yeah. So here's the deal. Dan did the code. So they needed somebody to do the stress test and find out where it worked and where it didn't and how it behaved and what
To
the
verify the model system.
right. And
That
I
the
was
analytic model was following the empirical model. Like,
yes.
once we test it, is
And
this
and where it
matches, and it
departed
matches,
and by how much.
and right, so
Okay.
that they could maybe tweak. Got
And
it. Yeah.
I was that guy.
So that's how you came to do the project. Is that correct?
Yes. And so it turns out that you start out with these are the aerodynamics that I want. What's the shape? Now stop and think about what I was doing. I had Prandtl 1933. Prandtl describes the aerodynamics that you want.
Right.
He does not describe the shape of the wing.
You mean as in plan form? You're talking about the actual wing shape.
None of it.
Right. Okay. All of
Prandtl
the
is
above.
only talking about the span load, the load across the wing.
Right. Yeah. So it
He
doesn't really
does,
matter the shape in his mind.
right. The shape could be anything. How do you design what that shape would be to give you that span load? And it turns out that you have to make these simplifying assumptions. You throw things out, and you hope
Naturally.
that isn't something that isn't super important that
Right.
causes you to fail on what you're doing. And so that's what I ended up doing. I created the inverse model for designing wings from Prandtl 1933. This is like one of the only things that I actually will take the blame for.
The blame.
But I don't even know how to. There's a lot of things that we look at when we're looking at your paper and some of the other things. I don't think it's really well understood how big a piece that is that you just talked about. I mean, I know you know it because you probably struggled with it before you figured out how, right?
17 years.
17 years in the hole I spent.
So let me give you just a taste of what that was. All right.
Yeah, please.
Here, this is
Yeah.
Prandtl. This is the second flight of Prandtl 3.
It's
This
so
is on
beautiful.
YouTube. And
Yeah, thank you, by
big,
the way.
big high start. You can see when the parachute falls off right
Mm-hmm.
there.
Yep.
And you can see the control surface deflection and just the graceful way the thing flies. Red's feeling it out. You know,
Yeah. Yeah, and one of the things in the most recent video, he does talk about how, and it's something I didn't think I would really get, but how as a pilot, you're moving your sticks and then you're watching how the plane's reacting. And through that, you get a feel for the plane itself and its flight characteristics, which is funny because when you talk to a full scale pilot who's in the plane, who can physically feel, they're feeling the reactions of the rudders and all the other things as they move. Those same feelings we have similar experiences, but it's a very different.
right.
Yeah, it's a very different
And
methodology to get there, but we come up with the same response, same feel.
Red is one of those people that has both.
He's awesome.
Right.
Big fan of him. Big
Yes.
fan.
Yeah, get in line.
I know, right? I know I wasn't the first. I know I won't be the last. So, oh gosh, and it probably took forever to land. That was one of the
I'm
things
about
I
to
was
say, it's
looking at.
sitting there in that ground effect forever.
Ever. It only.
Red hated that.
I know, right?
And
Well,
I loved it.
because you don't want to, but you don't want to push it. Like you're trying to get it down. You want it to land not too far away. So you're trying
Right.
to push it into the ground, but you don't want to flare it because then it stalls and now you're having to rebuild a plane. You don't want to
Yeah.
push into the ground because then it crashes and you have to repair something. It's so cool.
Lead
That's
off and finally settle.
one of the things I was reading, Nest of Dragons. We talked about them earlier. They
Yeah.
have a whole section on the Prandtl wing. They have a section on you very specifically. I know you worked with them on some parts of the project. One of their first goes, their response was, "We need to add spoilers to this right away because otherwise we keep missing our field." Like they were coming in for landing, like this doesn't land. We need to do something about this. So they're like,
Right.
put a spoiler on the top like a glider, and that's the
That's
only
right.
way. You gotta spoil the lift, otherwise there's no way you're gonna get it down.
I design them to stay up. I don't design them to come down.
I know, right?
Well, you did that well.
Yeah, well done.
So, um, one of the things that we have at NASA is this cFOSS system, fiber optic shape sensing. And so we can look at how much the fiber optic stretches or compresses if the fiber optic is glued to the upper and lower caps of the spar.
Ooh.
Now okay, now you get it, right? And
As
so,
a structural engineer, that's really exciting.
okay, so now if you know what the shape is, you can back out what the load is, right?
Right. Yep.
That's what I thought I was going to be able to do, and I couldn't do it. I'm just not smart enough. And we, I understand now what I need to do in order to make this work, but I just couldn't get there.
Okay. As in, so you were discovering the linear deflection as a whole on the top and bottom spar, or was it
Yes,
along the way as well? Because you put in a
every one
million.
centimeter.
Okay, because you put a million fibers in. Okay, that makes sense.
No, one fiber,
One fiber.
every one fiber, and every 1 centimeter had a Bragg grating. And you'd pulse a neodymium YAG laser, and the pulse would go down, and then you'd get these reflections from each one of these Bragg gratings.
Ah,
And
okay.
at the speed of light, you would be able to separate those out.
Right, which is what those
Okay,
pulses are showing in your data there.
exactly.
Oh my God.
Exactly.
This is not in, at least I didn't look at the paper that shows any of this stuff. This is really exciting to me, especially as you
Okay.
explain it so we can understand it.
Okay. So I eventually gave up on this. And in retrospect, I know what to do now,
Hmm.
and I could have gotten better results. I didn't. I gave up on this one, and we went back and we had pressure taps in the other. So this is the right
Yep.
wing. The left wing, we had pressure taps.
To,
And so we built a pressure sensing box. And
yeah, I saw that.
each card had 32 pressure ports on it, pressure sensors, okay? And
Right.
then Beagle Bone Black on each of the 3 cards. And then we had what was the system that would write the data? I can't recall.
Okay.
And
But it would sense
uh,
the pressure differential and
yes,
record it every so, like, whatever time.
and we wrote it to an SD card.
Okay.
And so Red made these beautiful little 3D printed pressure taps flush on
Yep.
the leading, on the upper surface and lower surface.
Did I mention he's
And
awesome? I think I did. Go ahead.
yes, right. And all the names down there in the lower right, those are the students that actually designed this system and made it work.
We're gonna,
And
if you don't, I'll remind you later. But these pictures, if we have them, we can kind of replace what we can't see. And we'll
yeah,
picture that.
yeah. I'll send these to you.
That's perfect.
Okay.
Keep going.
So calibrations, the span load. So this is the pressure data. And you can see the span location, 0.1, 0.3,
Hmm.
0.5, 0.7, 0.9. And you can see the area between the upper and lower surface, the red and the blue, okay?
Hmm.
Is that
So
above the wing, below the wing?
the top of the wing and the underneath the wing.
What is the point one? Is that the distance from the cord leading edge? And that's along the
No,
cord?
it's along the span.
Okay. So point one
Be,
is 10% out.
yep.
And then those points that we're looking at are along the cord line, both
Right.
top and bottom.
Okay. And if you look
Okay,
at
I
the
just want to
area
make sure I
on each
understand it.
one of these, you can see in your mind how this would taper down.
Yeah,
Okay.
of course.
As you went out to the tip. Okay. So there's one other piece of the puzzle here that I need to explain to you about this. Um, I'm telling the kids to put this together and how it needs to be displayed, and when we get this data, and they're we're taking swaths of data and then we're averaging all of it and we
Right.
get a curve. Okay. And so the other thing I forced them to do was to figure out the uncertainty based on
Right.
the data that we had. It's called Kramer-Rao, and it's a measure of uncertainty. And
Yep.
so I had them calculate what that uncertainty was for each of the data points from the root to the tip. So then I took the Prandtl 1933 paper. And by the way, when you look at it, it's a fourth order equation.
Gotcha.
Can you give a
Okay.
quick definition of that for me?
Okay. So fourth order equation, you have x to the fourth, x to the third, x to the second, x to the first. And you're multiplied by the you have a coefficient on the front end of each one of those.
Yeah,
There's a
think of like
rule in
ax squared plus bx plus c is a typical, what is that?
exactly, right?
Right.
Okay. So
That's
now,
a second order equation. Fourth order
right,
means, so when we do deflection calculations in structures, they tend to be fourth order.
right. Okay. So there's a rule in mathematics that says how many data points do you need in order to solve for the order of the equation? So a
Right.
second order equation requires 3 points. A
Yep.
third order equation requires 4 points. Okay. So this is a fourth order equation. So how many points do you need? You need 5. 0.1, 0.3, 0.5, 0.7, 0.9. We had 5.
Okay.
So you
And
were able to solve for the uncertainty.
yes. And so my hope was that when you compared the Prandtl 1933 with the data that we recorded, that it would like be close, you know?
Right. It
I
resembles
mean,
something. Right.
right.
Now move your head to the left a little bit. There we go. And there it is. It crosses the zero at what, 0.9?
All the way out at 1.
Yeah, okay. Yeah, that's where it hits zero on the red.
Okay, and the red was Prandtl 1933.
Yep.
And then your data with its
Are the
uncertainty is like almost dead on it.
the black dots.
I mean, straight out dead on it.
So
You couldn't ask for better results.
You really couldn't have.
people were sure that I had cooked the books when we got this.
Well, then you
And
give them the 2 million data points you had and said, here you
yeah,
go. Right.
well,
I know
when
that's not
when we
solution.
published this stuff, the thing I said was, go build one of these things and fly it. And if you get different data, let's talk about it.
Yeah,
But
love
I
to
am
hear it.
convinced, I am convinced that, and by the way, this is in the second report that we put out in, what was it, 2021?
Right. Yep. Yeah, you had one, I think, what, in 2017, is it?
In 2016. Yep.
2016, right. And then there's a follow-up paper. The first one is we'll have a link to both papers.
Yeah.
I have them both. I've definitely created a link for them already. So if I can find it, I'll tell you. But yeah,
this was my, I couldn't believe that we got that.
it's
And
on wings of minimum induced drag span load
yep.
implications for aircraft and other things that are off the screen and aircraft and birds.
We
Is the
have
first one
that got made into a hang glider. It's flown 8 flights, but has not flown in several years now.
What I could see almost immediately like that. I know I don't know much about testing aircraft to truly understand its regime, right? Because the difficulty with brand new aircraft and new ideas and new systems is you want to understand what it'll do, and you want to do that safely, right? You don't want to just throw it in the air. Hey, look, I can put a propeller on this. This looks great. We'll just keep flying it. It'll be, and then you get that one condition where now you're in an uncontrolled spin. You can't get out, and you have to either bail or pull the
Right.
parachute, right? And that's the situation nobody really wants to get into. That's why experimental aircraft concerned a lot of people,
Right.
because it's not tested well enough generally. But at the same point, like there's ways to test it. So you're like, look, I've gone through almost every situation you can think of, other than, I don't know what, frosting on the wingtips or whatever. You know what I mean? Like you can go through most regimes pretty quickly. There's a fairly methodical way to do it. So anyway, so he's at 8 flights on that. I'm sorry.
Flies so magnificently, it's not even funny.
It flies exactly like the model.
Yeah.
It's incredible.
And for lack of a better spot to put this in there, Rara Brian did want me to bring up with you at some point, just so you know, like all the inspiration that you and this have caused and generated.
Yeah.
We have a plane called the Noob Wonder. Sorry, no, he did the Flurkin, didn't he? He put it on the Flurkin.
No. It was the Noob Wonder.
Okay. I didn't want to get the plane wrong, but we have a plane called the Noob Wonder.
The one that's got the Hulk right here on it. It's a Noob Wonder. It just basically has a different tail section than a Sig Wonder.
Yeah. He put the Prandtl wings on that and loves flying it because of how it handles.
Yeah.
Yeah, so there's some folks out there just putting Prandtl wings on stuff just to see what happens.
Yeah, and I was telling Al earlier.
I love that.
Yeah, I'm like, well, let's look at this thing. I said, what are we trying to actually do with the twist, right? The twist is to get just enough rotation of the cord so that the thrust line is forward. So when it gets into that regime where we're putting one versus the other, it actually creates a forward thrust on that upward wing, right? So you don't want it too much, because then it really creates a ton of drag and it negates any thrust you might have gotten, right? If you twist it too far forward. If you make it level, the thrust line is straight up or backwards. So that's not going to help, right? Or if, and there he goes. If you look in the side chat, you can see what he did with the plane. It looks great. But thank you, Rawa, for posting that. And so what we talked about is the Sig Wonder has like a 4-degree, it's a symmetrical airfoil, but it sits at about a 4-degree angle of attack, right? The propeller is actually down a couple degrees and the wing sits at a couple degrees up. So the net is about 4 degrees angle of attack. So I told him, I said, look, let's twist the outer sections, because he had twisted really far. And he's like, this is a weird, spaven weird. I'm like, shallow it out to like 6 degrees so that the outer wingtips are at -2. And let's see how that flies. And then he flew it. And he said it took a minute to get the CG because, as you discovered in the original model, it's not where you thought it was going to be. So you want to talk about that really quick?
Yeah, we thought we knew where the CG would be based on the elliptical span load. And it turns out it's not elliptical anymore. Duh. And
you don't have lift all the way out to the tip like that.
Yeah, so we ended up with the CG in the wrong place, and it was just it was miserable. I mean, we were just crashing the vehicle every flight.
As we say in the RC world, a tail heavy craft flies once.
Right.
A nose heavy craft will fly poorly multiple times.
Yeah. And so we put the CG way out far forward, and we have this great big steel nose boom with a bunch of really large steel nuts bolted on the front end of it. And Red started taking the nuts off and, moving the CG back, and it flew better and better. And
Yeah. Yeah, I know when I looked at it, I'm like, well, if the transition of upward, we'll call positive lift versus the forward twist, right? That inflection point is at the 70% mark. I'm like, what if I did my CG calc, assuming that's the tail, that's the tip of the wing, right? Because that is where the lift bell curve stops, more or less, right? Because then it kind of tapers out and it levels out to the wingtip. So I'm like, if I do my calculation there, and I did the rudimentary, like, where you add the inner cord to the front and back of the wingtip, and then the
I
wingtip
hate to
cord to
interrupt
the
right now, but
yeah. Look
watch
at
the
that.
pilot's hand. You, did you catch it? He
What did
lets
he
Grabbing
go
do?
of the
something.
stick.
Yeah, he just
He
let it
lets
fly
go
to
of the
sea.
stick, and there's no response. There's no. I mean,
Yeah,
he just lets go, and it keeps right on, just like it
yeah.
was meant to be there.
When you're well, at least
Sorry.
flying mine, I have a little bit of dihedral in mine. It's a planker, so there's not any sweep, which would make it even more stable. But when I'm in the center regime, when I'm relatively flat like he's flying, it just wants to hang there.
Yeah.
I mean, it really doesn't want to come. I mean, it's easy to get it out of it if you want, but it does want to stay there naturally. It's pretty cool. And obviously that's what he's seeing. That's beautiful to watch. Really. You must have been so proud to see that go. How did
Well,
that feel when you were doing that? When you were loading up, were you getting anxious about his safety, or what were you
yes,
thinking?
I was terrified. I was terrified. I was really worried that, s- something that we missed, and, you know,
Yeah.
maybe something unrelated to the span load. And but
Right, a control regime you couldn't get out of or something.
yeah. So Red was there
So,
this day. Um, Steve Slaughter, he was a former scaled guy.
okay.
Um, ended up working for Lockheed for a while too. And then this is Steve Davey that's flying. The owner and builder is a guy named Eric Chase. And Eric is a sailplane pilot. That line he put on is the spoilers. And the spoilers are too close to the center. So there's a large pitch change.
Mm.
And
Yeah, yeah. I mean, that's where the biggest lift is, right? If he'd put it about mid-span, I probably would have
right.
had a much more gentle. I'm sorry, I'm just watching. It's
That's as pretty a touchdown as you can really ask for there.
yeah, really.
I don't want us to overblow our welcome with Al. We've had him for
Yeah, thank you, Joe.
quite some time, and I know that we will. Matt and I can talk for hours and hours, and I know Matt would love to pick your brain for hours more.
Sorry, Al.
But I don't want to overstay our welcome in this generous time that you've given us. Um, Matt, do you want to quickly look through any of the questions?
Yeah, one.
See if there's any that need to be wrapped up.
Do you have any one of the quick questions was in the lifting body airplane, that testing of the lifting body, which is probably the first aircraft tested at Armstrong, which was not originally Armstrong Research Center. Um, did Armstrong actually uh, fly that at all?
The lifting bodies?
Yes.
No, no.
Okay.
Neil left during the uh, X-15 era. And it was funny when he got down to Houston, um, they considered the X-15 to be um, flying into space. And so they viewed his being there was more of a lateral move than a step up to become an astronaut,
Mm-hmm.
which was kind of an interesting thing. Yeah, no, Neil never flew a lifting body.
Okay.
He was a sailplane guy. and he loved talking about airplanes. He never wanted to talk about flying in space.
Yeah, and that makes pretty good sense. Were there any competing theories to or models regarding any of this kind of stuff? If so, did they compare? Were there any comparisons?
There were a couple. None of them were really serious. So
Okay.
R.T. Jones, the two great researchers within NASA for airplanes were R.T. Jones, um, and the oblique wing was his thing.
Okay.
And he also played around with this span load a little bit. And then the other one is Dick Whitcomb. Whitcomb came up with the area rule, you know, the Coke
Right.
bottle shape on the 106. He came up with the supercritical wing, and he also came up with the wing cut. And so Jones
Right.
and Whitcomb were like, by the way, one was West Coast and the other one was East Coast. And I actually met R.T. Jones at a wind tunnel test for the oblique wing. One of those amazing things. NASA was just like that. You'd be walking down the hall and a buddy would grab you by the collar and drag you into this conference room, and all of a sudden you're talking to Neil Armstrong.
Right.
It was just that kind of a place.
Was it a kind of thing where you felt like a little starstruck, or was it just, oh, it's another day at the center?
No, it was
Starstruck.
your jaw hit the floor every single time.
Okay. Yeah, that's fair.
Chuck Yeager walks in the front of the hangar door, and just walks up to you and says, "Hey, I'm Chuck." Shakes your hand.
Did you ever get attention by those guys with this concept that you were testing?
No, I didn't get to that point while any of these guys were there.
We're there. Yeah, I know, but I recognize that they are, relatively speaking, not all of them are even alive at this point.
Yeah.
Right? Just because, it's
most
been
of them are gone now.
50, 60 years ago.
Yeah.
So, they're all in their late, 80s and 90s, if we're lucky.
So one of the rookies from the very last Apollo mission was Vance Brand. And Vance stayed on and flew the shuttle 3 times.
Nice.
Really?
Vance is a friend of mine.
Nice.
So I guess I wonder, like, if one of the questions was talking about, this is one of the few, and I think this is part of what excited me about this whole thing, is that there are very few. It feels like there are very few new aerodynamic concepts. I mean, this one is honestly very old, right?
True.
But the question is, I mean, are there new concepts coming through still, or are we feel like we've hit the edge? And there's not much more to do except refinement.
I'm going to say, the instant I say this, I will be wrong. Okay?
Is it a good thing to be wrong about? Go ahead.
This is something that's a very good thing to be wrong. I feel like the number of ideas that remain are coming to a close.
Mm-hmm.
This is one of the last big ones that's out there.
Why was it ignored by his peers at the time?
Why was it ignored by him? I mean, he never did anything with it for the rest of his life. Jeez. 1933 to 1953. And we've tried to figure it out. 1933 was a very chaotic year. That was the year that the Nazis came to power in Germany, and all the Jewish professors started having to head for the door. And Prandtl thought this was just outrageously wrong, because these were his friends, and he knew that they had brilliant ideas, and that the collaborative work that he could do with them would not happen. And because of some political madman that was in control.
Right.
So.
Yeah.
tying into that question of, or piggybacking off of that statement of, we may be at the closing in on the end of the last great ideas in that space. Challenge out to all the young and aspiring aerospace engineers. Go prove Mr. Bowers wrong. In that effort, I think the last question comes from one of our younger fellas, and he's asking, do you have any tips for an aspiring aerospace engineer?
Yeah.
It's a good one to close on.
NASA is still a great place to work if you can get in the door. It's getting hard right now, and I fear it might be getting really hard for a while. That they're not going to be allowed to replace people that are leaving for a bit. There is so much out there still to do, and so if you want to spend time at a university and work on this, there's almost 200 students out there that worked on this with me, and they're looking for ideas. I'm working with a kid that's we took a Hershey bar wing, okay, no taper, and we twisted it so that it would have this span load. And the reason that we made a Hershey bar wing like that is because he is covering the upper surface with solar panels. And he's making a solar powered airplane out of it. And so he wanted surface area.
Right.
It's like, okay, we can
Hershey
do that.
bar it is. Yeah, when your solar panels are not flexible and they're rectangular, you kind of get limited. I mean, I've seen some that are, we'll call it, they're delta shaped. They're soft delta, but they're a delta. And you really have to do a lot of stepping and you lose surface space.
Right. Right?
Yeah.
And so I helped this kid out with the shape of the wing and the airfoils and what he should end up doing. And he wants to go out and break the 168-hour record that's out there right now.
Wow.
Right. Yeah.
Right?
I thought there was like an 8-day.
Yeah.
That's
168 hours, isn't it?
I'm sorry. I don't do my math. It's too late for my math brain to do.
You're an engineer.
I know. It's also like 1:30 here, so my brain shut down like at 8 o'clock.
I'm sorry, guys.
That's okay. No.
Blame him, because no, it's good. We're accustomed being up this kind of late. I do think we are, if anything, reaching the tail end of acceptable decency in the amount of time that we have taken from you.
No, I think I have two questions, I think, that I feel are a good close to this whole conversation. You spent your life as an engineer working in, with, and leading teams, right? At different levels. What do you find was your most rewarding time? Was it leading teams? Was it being involved with teams? Or was it supporting them from, we'll call from DC, where you're ensuring that these teams have what they need to go forth because you're doing the hard work of convincing, DC yahoos to give you all the money that they need, that kind of thing. Where did you find the most reward and why? That's hard.
So solving 9-dimensional arrays, solving the stretch in a rope that results in a certain natural frequency in the aircraft. You could see the F-106 towing the C-141 around because of the stretch in the rope. Solving the span load on this little glider. All of those pieces were like those. I only solved 5 problems in 37 years with NASA. I only solved 5 problems in 37 years.
Wow.
And I lived for those days when you could say, you could put a, put a stake in it and say, this one's done. Here it
Yeah.
is. And Prandtl isn't there yet.
But
It's
there's
got,
more to discover.
there's more out there that needs to be solved on this particular problem.
Yeah. There's no is there a Prandtl designer where you kind of something that can kind of calculate the correct twist and position of stuff? Like, so I'm thinking in the term of a modeler, I want to build a plane. I want to do this thing. I want to get this flight characteristic, right? Is there something I can use to help guide me?
There are 3 guys that you need to go talk to. One of the 3, okay? And Anirudh Minaj, the Indian kid that's in the UK, 3.5. Okay. There's John Badilski, and he's at NASA Armstrong. And then there's Lauren Newton, and he's getting a PhD at Stanford.
What was his name? Her?
Lauren Newton.
Okay.
I'm told no relation, but anyway. And then the other half that's out there is a kid named Jesse Brady, who is a controls engineer actually at NASA Armstrong. He's up in Alaska right at the moment, but he was
Okay.
one of my interns, and his mom and dad still blame me for the fact that he works down here.
Fair. Okay, I'm looking to see. I'm looking
I
at
think,
our
yeah,
yeah.
I think we're probably pretty good there. And
That's
for the
good. No,
and for the
I'm
sake of
looking at how many
time,
people.
oh, okay. And for the sake of time, we will forego the traditional lightning round.
Yeah,
Thank
yeah.
you.
Usually we have a lightning round of 10 questions mostly regarding RC, and it's basically a this or that mess, right? Where we're like, okay, SR-71 or F-117, whatever, this or that kind of deal. And you're like, I don't know. You're like, choose one. Like, I don't know that one.
Sir 71.
There you go.
Perfect, wonderful.
Well,
Oh,
we'll get that
thank
with
you.
you next time if you grace us with your presence again. If we haven't completely ruined the experience for you, um,
I
we
hope you had a
really
good time.
appreciate.
Really.
It was good, gentlemen. It's
If
an honor.
Yeah, that
it
seemed it's
it's
more our
ours.
honor. Thank you. Yeah, really, in a big way. Joe,
Is there anything that
ooh,
we've
good question.
missed that we should have discussed with you or asked you that you want to bring up right at the end?
Oh, when I was doing this with all those students, I'd go to lunch together. I would assign myself a cube out in the cube farm with the students every summer. And we would sit down and we would have conversations about why are they making me learn this type of math? And it's like, okay,
Hmm.
let's sit down and talk about why they're teaching it to you in the way that they're doing that. We'd have those conversations and it's like, oh, okay, now I get it. And
I'm never going to use this math in the real world.
Oh
yeah,
man, I hear
and
that all
and
the time.
and then you get this. Yeah, I needed 5 rows of pressures because it was 4th order equation, and yeah, those kinds of things and those kind of moments. Um, I'm still on a committee that sends science experiments to the International Space Station. And the people who are sending these science experiments are high school kids. I love working with those kids because there's so much that they don't understand and know yet. And I'm trying to like put up the guardrails so that they don't go and do something dumb where it turns out to not be successful for them.
But they're
So
also
Right.
not held back by previous.
Yeah, that
You know,
preconception where, well,
Right.
I've seen this before, so I have to go that direction, as opposed to they
Yeah.
don't have anything. So it's like,
So
no, we should climb the tree over there. That's how we're going to get there. And you're like,
I try and
okay.
leave the guardrails as wide as I possibly can. Yeah, and
Right.
by the way, the school that I'm working with that does this, they've done this 22 times, and I've done it with them 17 times now. I can't stop.
Why should you?
I love it.
I mean, honestly,
love
right?
seeing those brains work, man.
Yeah, that's really incredible. That has got to be some of the most rewarding stuff you could do. I mean, I know it's all
Oh yeah.
rewarding,
Oh
but you
yeah.
know, there's something about seeing the spark, seeing that light bulb light,
Yeah.
that sudden real, and I'm sure you saw it with your students when they were working with you on the thing. They're like, wait a second, wait, we're doing this because of this. And you're like, you got it. You got it. And then they're
The
like, wait,
the
yeah,
best
it's so
ones
cool.
are when their experiments come back from space. There's inside the box is this little tiny package of plastic package that's taped inside the box, and you pop the package open, and there's 6 patches in there that have been to space, and each student gets a patch to put on a flight jacket.
Right. That's so cool.
So cool.
So cool. Thank you so much. Thank you so much. Joe,
Gentlemen,
are you ready to take us out?
Let's take us out. Matt, I'll say hold the details for the prize drawing until after the outro. And I'll
Okay.
say you can record a bit afterwards and we'll put it in post. So, guys, listen
Sounds like a good plan.
to after the outro music to hear details on the drawing, the giveaway for that that plane
For
from
the gladiators.
Gladiator. There it is.
We're gonna send a gladiator kit with the electronics to 2 lucky folks,
Well,
one of
now
which
you're
has been
talking.
here asking questions. I'm sorry. And then when we get to the YouTube, when we post to YouTube, we're going to ask for, give us ideas. This is a way you can win a second chance. Give us an idea for our next episode. Post it in the comments below, like, subscribe, and then we will pick from that group of people who did that. We're going to select a random one and we're going to reach out to you and send one out to you.
Okay.
I'm done. I really
now I
promise.
can do the outro? Okay.
Yes, please.
Well, guys, as always, we thank you for tuning in and listening. We hope you have enjoyed this 100th episode. We weren't sure that we were ever going to get there, but we hope you have enjoyed it as much as we've enjoyed sitting here with very special Mr. Al Bowers. Thank you so much for your time and hanging with us and just being an awesome guest. It has been an absolute honor and a privilege to have you on and to be able to speak with you. Two yahoos that kind of have an idea of what they're doing, but mostly don't. So thank you.
But we're in a quest for knowledge ever so.
If you have questions, thoughts, comments, concerns, feel free to reach out to us. You can reach us at aviationrcnoob.com. You can swing by the Facebook page or drop into the Discord server where maybe you'll see Mr. Al hanging one day. We don't know. Link will be in the description. You can also swing by the website. We do have a contact us form that last I checked it works, but the link on the website has been updated so that it works.
Oh,
Yep.
it works. The problem is it works.
Oh yeah, it works too good. We get Sherry
Well, we'll
from
have to
so
work
and
that.
so. Let me be your
Yeah. Oh my
marketing
god.
person.
Oh
Yeah,
my
thanks.
god. Well,
But
anyway,
the Discord link on the website has been updated, so somebody had
great.
reached out to us about that. That's been fixed. Yeah, episode 101 sometime in the next little while. We've not been so great about doing that every month thing like we were talking about, but we will. I assure you, eventually get back to the every other week.
Yeah,
Life
that's
has
coming.
just been life, but we are hopefully getting towards the tail end of that and we'll be returning to normal. Thank you for the guys that have turned up in channel to join the conversation, at least in the text chat. Lee, Brian, Richard, we see you guys out there. Thank y'all
Yeah.
so much. And if you've got nothing else,
Nope. Just remember, this episode has been sponsored by Windcatcher RC. And that's
by the
it.
patrons.
Bye.
Al, thank you.
Yeah, thanks a lot, Al. We really appreciate it. Oh, what's his wow, now I'm gonna blank on it. Mr. Patrick Murphy says hello, by the way. I know he came out there to visit you guys a while back, and he's like, "Oh my God, you have Al, and I love Al. It's great." And I'm like, "You should come on and join us." So I'm surprised he wasn't able to make it tonight, but he
Very cool.
definitely sends his hello. Yeah, yeah.
Awesome.
He's a really cool cat. He's just a great character, you know.